Welcome to this explainer. Today, we're diving into the Davison-Germer experiment. Now, this isn't just some dusty old science lesson, right? It's actually a thrilling scientific detective story that literally flipped our understanding of reality upside down. We're going to look closely at how a single, incredibly elegant experiment took our everyday common sense, threw it out the window, and proved that the universe operates in ways we could barely even imagine.
Think about it for a second. What if the solid matter making up your world was actually a wave? I mean, it sounds completely absurd. You knock on a wooden desk and it feels entirely solid. But we're going to start right here with this provocative question to set up the ultimate twist of quantum mechanics. Because as you'll see over the next few minutes, the physical world is far stranger than it appears.
All right, let's get into Section 1, Particle Assumption, the classical view. Okay, so to really grasp this breakthrough, we first have to rewind and look at the classical scientific consensus. For the longest time, the rock-solid belief was that an electron was only a particle. Think of it kind of like a tiny, solid billiard ball. It has mass, it takes up space, and it moves in predictable, straight physical lines. This was the absolute foundation of how scientists understood the microscopic building blocks of our universe, the whole shebang.
And while this makes total sense based on our everyday experience, right? It sets up a really clear baseline expectation. If you shoot a physical particle at a wall, it simply bounces back. It hits the surface, it scatters off, but it remains a solid object bouncing off another solid object. If electrons are purely particles, they should just bounce off surfaces with absolutely zero wave-like behavior. None.
Moving on to Section 2, the electron. Experimental setup.
Let's transition into the investigation phase and walk through the brilliant simplicity of this experiment. It's basically 3 steps. Step 1, you've got an electron gun, which produces a steady beam of electrons. Step 2, a nickel crystal is placed right in the path of that beam to act as a diffraction grating. And finally, Step 3, a detector is set up nearby to precisely measure where those scattered electrons go after they hit the crystal. So, the experiment is officially in motion. A beam of electrons is fired from the gun, it strikes the surface of the nickel crystal and reflects back. Davison and Germer are just sitting there watching their detector, waiting to map out exactly where these tiny solid particles bounce. They are fully expecting a simple scatter, but they're about to see a completely shocking anomaly.
Which brings us to Section 3, the wave pattern, the impossible anomaly.
Now here comes the massive twist. What's really interesting here is the stark contrast between our common sense expectation and the mind-bending reality. On side A, if electrons were only particles, as expected, there should be no wave pattern whatsoever, just a random, predictable spray of bouncing objects. But look at side B. What actually happened? Diffraction occurred. And here's the kicker. Diffraction is a property of waves. Solid particles simply don't diffract.
But there it was, right in the data. The reflected electrons formed a diffraction pattern perfectly similar to waves. I really want to emphasize the sheer shock of this anomaly. It literally broke the known laws of classical physics right there in the laboratory. Instead of bouncing like solid objects, the electrons were interacting with the nickel crystal and spreading out in an interference pattern. They were showing us matter acting exactly like a wave, no way around it.
So the crucial takeaway here is this brilliant concept of wave-particle duality. This is the confirmed reality that matter, such as electrons, behaves like both particles and waves. It isn't just some philosophical musings. This experiment proved that solid matter isn't quite as strictly solid as we thought. It has a true dual nature, possessing mass while also literally waving through space.
And you know, this unexpected diffraction wasn't just a random fluke in their equipment. Why? Because the measured wavelength of these diffracting electrons perfectly matched the de Broglie wavelength. Prior to this, a physicist named Louis de Broglie had proposed the mathematical hypothesis that matter could wave. Davison and Germer's experimental data precisely matched that theoretical math. They basically caught the universe red-handed, behaving exactly as the wild new quantum theories predicted.
All right, Section 4, Changing Physics, a Forever Impact.
Let's look at the profound historical impact of this discovery, because it accomplished 3 truly monumental things. First, it completely confirmed the de Broglie hypothesis, turning mathematical theory into physical fact. Second, it provided the very first hard experimental evidence for matter waves. And third, it heavily supported the development of quantum mechanics. Honestly, without this experiment, our modern understanding of the microscopic world wouldn't stand on the firm footing it does today.
In fact, the ultimate legacy of this experiment can be summed up in one clear line, directly from our source material. The Davison-Germer experiment proved that electrons behave like waves, confirming the existence of matter waves. That is the undeniable triumph of what they achieved.
But let's bring this home and look at how this shapes our modern reality. Because this is not just about a nickel crystal from a century ago, right? Matter can behave like waves, and wave-particle duality is absolutely real. That means the screen you're looking at to watch this explainer, the chair you are sitting in, and the atoms in your very own body are all subject to this exact same wave-particle duality. You're interacting with matter waves every single second of your life.
Which leaves us with a truly fascinating conclusion to wrap things up. If the very building blocks of matter, the electrons swirling in every atom, are literally waving through space, how solid is the reality you're standing on right now? Thank you for joining me in this explainer. Keep questioning the world around you, because as we've seen today, reality is always stranger and far more wonderful than it first appears.